Welcome to Chapter 12, ANOVA's second part, where I will briefly discuss some problems and to wrap up this topic. So let's move on to my spreadsheet problem examples. Here I will specifically discuss 4 or 5 problems with you, and that I guess would be sufficient to show how ANOVA table looks like, how to use it, and to for practical purposes, what each parameter and everything again means, and how to use this, most importantly, for hypothesis testing. So as I use the older edition of the textbook, I kind of put some problems out here for illustration purposes, ladies and gentlemen. And the first problem obviously talks about tuition charges, thousands of dollars in each part of the United States. As you can see glaringly how the tuition are so high, especially in the Northeast part, $40,000, and these are 5 private colleges in the Northeast US, 4 in the Southeast, and 5 in the West. Again, because there are 3, all total there are 4 plus 5, 9, 14. 14 number of observations is the number of observations, but we have 3 kind of treatment experiments, or in other words, 3 kind of treatments or sample data. So in that case, we will use the F-stat to do our hypothesis testing. The question being at the 0.05 level of significance, just seem like a right way to write that. Can we conclude there's a difference in the mean tuition rates for the various regions of the country? So obviously null hypothesis, mean tuition rates are the same, and mean tuition rates are not similar. You can use the textbook mu. I often show students, if you do not want to invoke your math symbols, one way to just write mu, you can say, well, H naught, excuse me, H naught mu1 equals mu2 equals mu3, where an H1, HA, alternate hypothesis, or H1, they are not equal. So mean tuition rates, where you need to, if you are putting mu, you need to say where mu1 mean tuition not this region, mu2 this in this region, and so on and so forth. So you must be able to define, otherwise just use the spreadsheet format that I'm showing you here. Step 2, level of significance. Step 3, use F-stat, because we have 3 samples here. Reject null if F-stat is greater than computed, if stat computed is greater than F critical. So one way of getting both the computed and the critical, as I showed some of the tables in the last video, is just have it do in Excel. Again, data analysis will also give you the ANOVA. Do not go with the 2-factor replication or without replication. These are replication studies. In many experiments, you replicate the studies, you take more factors, and then there are various factors, K times K, kind of like these. We are not getting into those complexities. So for each one of your problems, you just choose the single factor ANOVA table. So single factor will ask you to put the input range among 3 samples. Label in first rows, that's fine. Our level of significance, you can change this, but 0.05, as we all know, is pretty much default in Excel. And here, put your ANOVA table. Always put it on this sheet, and the single factor ANOVA table comes up. I always tell the students, you can also look at the p-value. This is something we will do in regression statistics more. This p-value at the 5% level, if it's less than 0.05, that means your results are significant. But you can also see the F-stat out here. 21.6, whereas if critical, and we do not have to follow the table here, it's just like the t-stat or the t-table that we compute with the pooled or the paired t-test. Everything is given. That's the best thing about Excel. So here the conclusion would be, let me write this down, based on the table values, computed F-stat is greater than critical F-stat. This, if you forget, please write computed. The Excel will not write this for you, just write as a note computed. And this is, of course, F critical. And so meaning we can reject the null hypothesis and conclude that the mean tuition rates are not the same. Another problem I'll show you real quick. I need a little bit of space out here. I set up the problems, everything for you, and these are already uploaded on Blackboard. You make them a little bigger for us to see. 5 from treatment 2, 3 from treatment 1, 4 from treatment 3. So 5 plus 3, 8, 9, 12 observations in total. Now we do not need to calculate all these in mind. We were doing this because we wanted those degrees of freedom. When we saw the chart, we could put it, but right now we can just go over to Excel to help us here. Single factor ANOVA. Wonder what this is. Uh-oh, one came over here. That's what. 5 observations from treatment 2. Treatment means are equal. A null hypothesis, alternate treatment means are not equal. Again, you're testing whether the alternate is correct or not. And if we can reject the null hypothesis, level of significance the same. So again, one more time, data analysis, single factor ANOVA, the first thing in your data analysis. Okay, input range. Please get the whole input range, ladies and gentlemen. Levels in first row, alpha 0.05, and I will try to put the little ANOVA out here. Do not mean to make these too little, but as you can see, by the way, the first table itself is kind of a summary statistics kind of table, how many groups, and then 3, 2, how many counts in each, the sum, the average, and the variance, etc., sample variance. And then you have the ANOVA, basic ANOVA table, single factor model. And I'm kind of beautifying it, which you can do actually to present your stats. And one of the things I would like you to do sometimes also take out the decimals to 2 places for our benefit. Making a non-numeric thing, so it was not doing it for me. So that's of course obviously shows that the F critical value is way less than the F computed. We can reject the null hypothesis and conclude that treatment means are not equal. A problem from ANOVA. These are trick problems. If you know the table well, these are incomplete tables, and I would encourage you to practice as much from your textbook if you want. Very little algebra involved here, as you can see. If you know the ANOVA table, this is a sum of squares. You have to fill out degrees of freedom for the SST is k-1, which is t. Degrees of freedom for SSE, we don't know, but we know that the total degrees of freedom is 11. So n-1 equals 11, meaning you have 12 observations, n equals 12, as I wrote here. That is a good thing you can do right at the start. So you know k-1 is the numerator degrees of freedom, that's 2, k equals 3, so you have got 3 treatments. So 2 here, and here you write 9. 9 plus 2 equals 11. And then how to get to the SSE and the SST division, the mean squared, the numbers, the summary, and then sum squared errors divided by n minus k, which is here. Actually, treatment mean, no, don't want to go here. SSC over N minus K. We know N, we know K. So SSC, if this is total variation is 500, we have the treatment variation and the random variation. Nothing is given to us, but we know that error SSC over N minus K, the second one, the error term, has a new denominator degrees of freedom N minus K. That's given to us as 20. So what is SSC if N and K are given to us? It's 180. So we fill this up so we know this treatment because 500 is given to us. As we all know, treatment variation plus random variation equals total variation. So that's the stuff we are using here. Little fill in the blanks. If you know this, then you can just subtract this 180 from 500 to get the treatment variation. And after that, just fill in the blanks again. We know SST over K minus 1. That's the numerator degrees of freedom. We know the values of the numerator degrees of freedom. K minus 1 is 2. Divide the 320 you got by 2. You get this. And F computed is just 160 over 20. That's the numbers we get here. 160 over 20. This is the full ANOVA table, and F computed is 4, whereas the critical value of F is 4.26. So if you have to do any hypothesis testing like before, you just reject the null hypothesis. The critical value, of course, here you have to take the table help. Let me see if I got the table here. I do not have it, but I guess that's where I found it, 4.26. Just go through the F-stat table, the numerator degrees of freedom on the top, denominator degrees of freedom along your right in the column, you will get 4.26. Remember the degrees of freedom here are 2 and 9. So use that 4.26 number. The next few problems are pretty much the same. I'm not doing it. It's kind of illustrates the same data. Yes, we just have to put in the numbers. And here I showed you the full table by showing you the formula in the formula bar. This is this divided by this is mean squared error, sum squared error, sum squared treatment, excuse me, divided by 2 is this. Sum squared error or random variation divided by degrees of freedom, this much. So I've computed this divided by this. And then from table, what is the critical value of F? Again, degrees of freedom at 2 and 18. Please check with the table. Let me know if you have any clarifications to do on these kind of problems. I did another one for all of you. If you have any clarifications, please do not hesitate to reach out to me. I don't understand the table value or something. Go over to the table. These are very mechanical. You just look at the tables, the computation you do yourself. The basic understanding, of course, is, do you understand how many treatments? Do you understand the number of observations? Do you understand the degrees of freedom you're taking out here? After that, it's mostly division, okay? And then again, carrying on our data analysis and putting our output in a representative form in Excel. Again, exam assignment questions will be pretty much like these. So feel free to go over these and ask me any questions.